Okay, we're gonna move on now to in this video to discuss the analysis of a deck. Before we go to the example, I will go quickly through this. Go to page, I believe it's 48. Look at the section provided analysis of a deck, and what it explains here is that you have three approaches to designing or analyzing a bridge deck, a concrete deck. One is a simple unit strip method. This is when the skew angle is less than 25%. Notice this is a bridge. If it has a skew, the skew angle here is less than 25%, then a simple unit strip method will be the best approach. If the skew angle is bigger than 25%, then it is best to use grillage analysis or finite element method. Grillage analysis is the next step of calculation, which you have to do your own calculation of second moment of area and properties, other properties, before you move on to the calculating the capacity. Finite element method, this is a more rigorous approach. Hand calculation will not be used. That's why most people use computer models, LUSAs, whether TEDs or LUSAs or MIDAS for doing this calculation. So therefore, you have a unit strip method, grillage, or finite element method as the method of calculation. Why the issue of skew is very important, because skew decks develop a twisting moments in the slab, which become more significant with higher skew angles. Computer analysis will usually give you the value of mx, my, as well as mxy, where mxy represent the twisting moment in the slab. Due to the influence of this twisting moment, the most economical way of reinforcing a slab, because of the moment under a skew bridge, then you have to design the bridge reinforcing in a typical ways. And it has been found that the best approach was given by Woods and Armour, how to design a reinforcement for a skew bridge, whereby you will be able to calculate, once you calculate mx, my, and mxy. And this is the appropriate way. You have a bridge here with a skew angle particular here, and then appropriate reinforcement will be straight up, and on the transverse direction, this is the way. Another approach of providing reinforcement is provided here. So that completes this. And now we can move on to the example. Provided for you there. Example H. Reinforced concrete deck design to British Standard 5400 Part 4. The problem here is provided that you design a simple supported reinforced concrete deck slab using a unit strip method. The deck carries a 100 millimeter depth of surfacing together with a nominal HA live load UDL of 17.5 kilonewton meter square and a knife edge load of 33 kilonewton per meter. The deck should also be designed to carry a 30 units HB load. The span of the deck is 12 meters center to center of the bearing. There's a graph here providing explaining to you. This is a 1 meter strip of a reinforced concrete, which is carrying a UDL and a KEL as provided, and you have a surface load part of it. You're also given various other data provided, the weight of the concrete, unit HB to be considered, based on British BS 8500. The class of the concrete is 32, 4, and 40 concrete to BS 8500. Also, the reinforcement is also based on BS 4449. From base British 851, you're also given data to include the class of the exposure, which is XD1. XD1 stands for what you call a class of exposure. I will discuss it a bit later. There are severe, there are moderate, there are, of course, extremely severe. And this one is particularly for a moderate kind of environment. So class X, D1 will be used at this. You will also find in clause A, point 3, the tolerance for reinforcement is 15 millimeter. And also table 5, A5 provide you the nominal cover for this type of concrete is 45, plus the tolerance, which is 60 millimeter. Then details for water cement ratio as well are provided. Now, how do you do this calculation? You begin by calculating the loading. That is the first step of the calculation. So how do you calculate the loading? You must calculate the permanent loading first. The permanent load is composed of dead load plus surfacing. This is the dead load. You are given already the value of the weight of the night, 25 kilonewton per meter square, and surfacing was 24 per newton kilometer square. This kind of data is available from the structural engineer's pocketbook in case you wanted to get affirmation of the value, but it's already provided for you. So based on that, you're able to calculate the weight of the deck, 16.3 kilonewton, the weight of the surfacing. You also move on to calculate the live load, HA and HB. Calculate which is HA UDL and HAKEL. You add them together, you get the value. And HB calculation, you know the value provided for you. It is 75 kilonewton per wheel, but per axle, an axle which has 4 wheels, it means that axle will carry 300 kilonewton, but for one wheel, it is 75 kilonewton. Once you calculate, you put those initial calculation, then you multiply them with the appropriate factors of safety. Combination 1 is here, combination 3, combination 1 and combination 3. Remember, in page 38, it discusses the various combination, and for the purpose of this course and this calculation, we will just look at combination 1. And the concrete factors of safety is provided for you here under combination 1. So notice that it is provided that combination 1 is provided permanent loading plus live loading. And combination 3 is permanent loading plus live loading per the effect of thermal or environmental effect. But we're not going to look at it at the moment. Because we're not dealing with the environmental or temperature effect at this stage, we're going to just skip through to move on to the calculation of dead load versus dead load and live load. Notice here now we're looking at combination 1. Dead load, permanent load is combined of dead plus superimpose. You will calculate them, add them together under two situation, which is the serviceability limit state and the ultimate limit state. So the dead load under design serviceability limit state is after you add them, you apply the particular factor of safety. It is 345 kilonewton meter. The design ultimate limit moment, you calculate it. It is 454. 454 kilonewton meter. Of course, remember in the calculation of moments, moment is always WL square over 8. WL 12 square over 8. That gives you particularly the moment. So the same calculation is calculated. Now you have moment and the serviceability limit state, moment and ultimate limit state. Once you finish with the permanent load, you come and start calculating the live loading. Live loading is combined of two loading. One is the HA loading, which we talk about. HA is also combined of uniformly distributed load plus knife edge load. You calculate this together and you get the moment. You come to the HB. Notice what we discussed in the lecture note, how the arrangement for the wheel, the four wheels, axle wheel for HB, which gives you this arrangement for one particular, this is one axle, one wheel is here, 75 kilonewton, and between the wheel, it's a 1.8 meter, then another wheel, and then there is a 5.2 distance, and then you have, I think it's 5.2, 1.4 plus 4.6, so particular 1.4, it's 5 meters, 6 meters. So because 4 plus 4.6 becomes 5 plus 1, it is 6 meters distance. So this now provides you with the arrangement. And based on this straight structural analysis, you're able to calculate the ultimate moment under HB. And this calculation was made. It comes to 392 kilonewton per meter. Now, what do? You come and factor, once you calculate the moments, you factor the loads with the appropriate factor of safety. HA loading under serviceability limit state combined with the factor of safety, it gives you 497. HB loading calculated with the factor of safety, it gives you 431, and you notice here is 431 is less than 497. Therefore, the most critical live loading is HA loading. Based on that, now you have already calculated the dead load and you've calculated the live load. You add them together, that gives you the total design load. For both serviceability, remember, both serviceability limited state and ultimate. So dead load plus live load, you add them together. That is the value of the moment. Also, for ultimate limited state, you add the dead load and live load moment, and it gives you the total loading. I'm going to skip through the combination 3 here because we discussed that's not necessary. We move on straight to how to calculate the reinforcement. Here's a graph, a nice graph. Now you know that your ultimate design moment based on this arrangement is 1137 kilonewton per meter. And I need to know what is the appropriate reinforcement. So you make an assumption, for example, try a 32 millimeter diameter reinforcement at 125 millimeter centers. These things come by experience sometimes. You know that you're dealing with a higher with a bridge which carry loads. At the same time, the span is 12 meters. Therefore, you probably need the higher value of reinforcement. So therefore, it's useful to use try a 32 millimeter diameter. Now, before we move on to this, you will see a lot of figures here. AS area of steel, FY the stress, the strength of steel, the strength of concrete, the lever arm Z. Where are these values coming from? So I'm going to take you to British Standard. As you can see here, BS 5400 part 4 clause 5.1.2.1 and clause 5.3.2.3. Let's go quickly to BS 500 to see what it is this provided. Okay, I'm just trying to get the British Standard here now. If you just bear with me a minute. Okay, close this one. We have maybe British Standards. Okay, I'll have to open that from. Okay. All right, I have now British Standard in front of me. If you open, if you can see, clause 5.3.2, it gives you all the equations. Equation 1, equation 2. Take notice of that. Ultimate limit, this is MU for concrete, MU for steel. What is MU? You come up here. MU is the ultimate resistance moment. AS is the area of tension reinforcement. A-S is the area of compression reinforcement. B is the width of the section. Fy is characteristic strength of the reinforcement. Z is the lever arm. So this equation, nice equations are provided for you in the British Standard. You take them and you replace the values. It's straightforward. You can see from the calculation here. So this is why I earlier said you need to have British Standard with you. You need to have BD, and then that gives you the best approach to calculate some of these. So using these values is straightforward. I replace for the two equation. You can see the first equation 0.87 Fy ASZ. 0.1, this is for steel, 0.15 FCU BD square, this is for concrete. Once you calculate this, you see that your moment capacity for area of steel is 1366 kilonewton meter. The moment capacity for concrete is 1977 kilonewton meter. I'm not going to use the higher value because that means the deck will crush under the steel reinforcement. So I will be using this my ultimate capacity for that deck and compare it with the ultimate moment you calculate. So notice here it is 1366 kilonewton meter, and before we actually calculated our ultimate moment, which was 1137 kilonewton meter. Therefore, 1137 is smaller than the 1366 kilonewton meter, or 1366 kilonewton is bigger than 13. Therefore, my reinforcement, which is 32 millimeter diameter at 125 millimeter centers, is appropriate. Thank you.